Welcome to a 20-minute video on Introduction to Aerospike. In this video, we will cover a brief overview of the Aerospike architecture and look at how Aerospike organizes its data. We'll look into capacity planning, the Java benchmark tool, which is used to load simulated data on Aerospike to get a measure of the latency you will see when you will load your data. We can also monitor the Aerospike cluster using the Aerospike monitoring console. So we'll see how that works, and then we'll go through a brief intro of how to connect to a cluster using a client, such as a Java client, and then do some read-write operations and also cover some of the advanced operations. So with that brief intro, let's get started with a quick overview of Aerospike. Well, folks, let's begin with an overview of the Aerospike architecture. Aerospike is a distributed NoSQL database. Aerospike stores records on a distributed set of server nodes, which is what we call our server. It's a cluster of nodes which talk to each other on the back end over what we call a fabric and connect on a front end to a host or a set of client machines through TCP/IP. The client machines run our client library that we supply to you, and the library does the job of talking to the cluster, and your application then binds to our library and you do read-write operations and other advanced operations with your data. So that is the basic concept. The way Aerospike is designed, and there are various ways of designing NoSQL databases, Aerospike is chosen to design in such a way that you do not get any hotspots by distributing the data. We take a hash of your key and then come up with a way to distribute every record based on 12 bits from that hash, giving us 4K, what we call partitions, and having each node in the cluster responsible for a set of partitions. This is what we call the partition map, and that allows the client to know exactly which node your data should go to. And it allows us to do a single hop to data without requiring any load balancers. This being a shared nothing architecture, you do want to make all the servers of like hardware and storage configuration. So when we distribute data evenly across all servers, a particular server does not become a gating factor. Also, in this architecture, the cluster is aware of new nodes joining the cluster or a particular node failing, and when any of those events occur, the cluster forms a new cluster with either a node removed or a node added, and it rebalances the data automatically without the need for user intervention and allowing the client library to serve data to the application through this process. This also allows us to do rolling upgrades where we can bring one node down and upgrade the server software wise while the clients are still live. So this along with the way we've designed it to prioritize all the thread operations where long-running tasks are prioritized in real time, you get a highly performant NoSQL database which gives you internet scale performance and is horizontally scalable. We also provide you a way to ship data to remote clusters of Aerospike. We call it XDR, or cross data center replication, which gives you an asynchronous backup of your data to geographically dispersed location. There are many ways that you can set up the data transfer, and you can set up on a certain segment of the data. We segment the data based on what we call namespaces, which is a storage definition as well as a policy definition of how you take a collection of records and segregate them by storage. So you can have multiple namespaces in Aerospike and then choose to ship certain namespaces only if you so desire when you are doing the cross data center replication. So with that brief overview of how Aerospike plays, let's look a little bit into the client. As I said, client is a library implemented as a jar or a DLL, and it exposes the operational APIs to your application. So that's where you will write your application. And at the back end, it's a first-class observer of the cluster. It is tending the cluster every 1 second by default and getting the state of the cluster by polling each node. It is aware of new nodes being added or any node failures, and it knows the partition map for each namespace. So it knows exactly where each record is, and that's what gives it the single hop to data. If I could generalize, NoSQL databases essentially are, at heart, key value stores. In case of Aerospike, we are a record store where the value can be one or more, what we call bins, which are equivalent to what we call, say, columns in a database. But in Aerospike, we have a record level schema. Every record is self-describing. There is no table level schema or a set level schema. So with that in mind, if you look at how data is organized across the cluster, you have a bunch of nodes and you define a namespace that spans across all nodes in the cluster. Inside the namespace, you can optionally have sets, which are nothing but a metadata on the records that belong to that namespace, and really a convenience in writing your application to segregate the records inside the namespace based on sets. So it's more of a data modeling convenience. It's not a storage or a schema definition. So sets have nothing to do with defining storage or the schema. Schema is defined at the record level and storage definition is at the namespace level. So think of sets only as a metadata. Records may contain one or more bins, and bins can have the following type: integer, string, double, binary large objects, lists, maps, or GeoJSON. With that architecture in mind, let's look briefly at how Aerospike distributes the data randomly. So when you define your key to a record, again, recall this is a key value store and you can choose to put your record in a set. If you choose to not put a record in a set, then null is used as the set name by default. And then we look at the type of your key value, whether it's an integer or a string or any other type. Based on your key type, your key value, and your set name, that is hashed using a RIPEMD160 hash function, which gives us a 20 byte value, and 12 specific bits of those 20 bytes become the partition ID for that record. So the partition ID is a deterministic calculation, and that can be done at the client library level. The partition allocation as to which node is a master for which partition and which node is a replica for a certain partition is decided at the time the cluster forms and is indicated to the client library when the client library polls each node. So the way the client connects to the server is that you give it a seed node, and that seed node provides the client library all the IP addresses of all the nodes in the cluster, and then the client opens direct connections to each node in the cluster and polls each node for its share of the partition map, and from that it builds the full view of the full partition map. And from this algorithm, it knows exactly which record belongs to which partition and therefore which node is the master. So when you read a record, the client library just goes to the master node. And when you write a record, it writes to the master, and the master in turn writes to the replica over the fabric. Inside the server, we maintain what's called a primary index of each record in RAM. So that's always in RAM. So that is the first place, based on the partition ID, the client library, when it approaches the server, say, find me this record at this partition ID. The partition ID forms the root of a red-black tree, which helps us look up the primary index of the digest, the RIPEMD160 hash, the 20 byte digest that you are interested in. Once we look up in RAM using the RB tree and we find the exact primary index in RAM, the primary index then contains the pointers to where your data is stored, based on whether you have decided to store the data in RAM or if you are storing in SSDs for that namespace. That's where it goes and finds the data. Aerospike's storage model therefore distributes data evenly across all nodes. You see, we write to the master and the master writes to the replica. And because the way we hash the primary key, the distribution is even across all nodes of the cluster. So that is how Aerospike distributes data evenly, and then based on a namespace, you can decide for a given namespace to choose data to be stored in SSDs or in RAM or in fact both. You can choose to store data in a file system on a spinning disk drive or a raw block device on an SSD. The flash namespace configuration is the secret sauce of Aerospike, where we literally give you RAM-like performance with persistence of flash. And as I explained, the primary index is where your operations come. You find the record metadata and the pointers to wherever you're storing your data, and the data is fetched or updated as per the API request. So that in brief explains the data storage layer and how we distribute data. Now let's take a brief look at capacity planning. So as I said, every record has a primary index in RAM. So depending on the replication factor you choose, and 2 is typical, and the number of records in the cluster, let's look at the capacity we need at the cluster level, and then we will divide it by the number of nodes to get each node's design parameters or capacity. So for the primary index, we need 64 bytes. That's a fixed size. So n times r being the replication factor and n being the number of records in the cluster, that'll be the requirement for RAM for a given namespace for the number of records you're going to put in there. So this is the cluster-wide RAM needed just for storing the primary index, and of course that times 64 bytes. So then if you're storing data in RAM, you have the formula for n times r, and b is the number of bins, v is the data size. So in RAM storage, so this is for storing the data in RAM, every object needs 2 bytes of overhead, 17 bytes per bin overhead for non-integers plus whatever the data size is for the non-integer data. And if the data is integer, you need only 12 bytes, and that includes for storing the data. And so that's for RAM storage. For flash storage, we do store all the metadata similar to what is there in the primary index on the SSDs. This allows us to rebuild the primary index from persistent storage should the node or the cluster go down and you want to cold start a node. So there is a little extra overhead there, and it has to be rounded to the next 128 bytes, because on SSDs we read data in 128 byte boundaries. So with that in mind, you can estimate the data storage for whatever storage you choose, either RAM or SSDs, for a given namespace, and then for the primary index. And using those three key parameters, you can estimate how much capacity you need for the cluster. And then depending on the number of nodes you want to deploy, you get the configuration for each node. Now, the other side of sizing to take care of is the SSD drives that you will use. In case you are choosing to do SSD storage, which is really the intended use case for Aerospike, to store data on SSDs, Aerospike publishes what's called the Aerospike Certification Tool, which lets you characterize the performance of an SSD. So before you deploy it, say on your bare metal server or even on the cloud, we have all those tests published which help you select the correct SSD, so you can achieve the desired latency performance. So capacity planning in a nutshell is not just about sizing, it is also about latency performance, and that is tightly coupled to the particular brand and model of the SSDs on your servers. So we do publish data on the recommended SSDs, and if you plan to use a particular SSD not in this list, the Aerospike Solution Architecture team can help you characterize it using our ACT tool. Well, with that said, let's look at how do you go about benchmarking performance. So with our Java client, we package what we call our benchmark tool. So once you download our Java client and unpack it, you can build the benchmark tool very easily, and it allows you to throw, let's say you have installed the server and you run the Java benchmark client on another machine, which we'll call the client machine, then you can start throwing load at the server. So the benchmarking tool allows you to specify the host and port of the Aerospike server, the namespace, the set name, and the number of records you want to load, which is that -k, the format in which you want to see the latency, the starting key, which is uppercase S. Here we are using an integer key starting with 1, 2, 3, 4, and so on, and we're specifying an object which is a string of 100 bytes, you have option to specify integer data as well. And then there is the workload, the -wi. When for the first time you're inserting records, you can do the insert workload, or if you already have records inserted on your server, then you can do an RU workload or read update workload, and that'll run forever and you can use it to measure the performance. This is a good tool to characterize the performance of your cluster, and you can slowly deploy the cluster into a production-like configuration while running the tool every time you change something in the configuration to identify any latency bottlenecks you might see. So here is an example how you would just run the benchmark tool to insert 100,000 records, and how the latency is seen as you insert the records, and that gives you an idea of what kind of performance you will get from the cluster. The Aerospike monitoring console lets you monitor the Aerospike cluster, and it has a dashboard which gives you a quick view of what's happening, how much RAM is being used, or the cluster usage. You can scroll down further and you can see at each node level how many objects are there, the expired objects, evicted objects, all sorts of useful information about the cluster can be obtained on the Aerospike monitoring console, or AMC as we call it. Now, as far as developing application for Aerospike goes, you're now in the client realm. So, the first thing you would do when you write your application is connect to a cluster. And like I said, initially you just want to connect to one node in the cluster, and just to make sure that that node is not down, you can give a list of hosts. So Aerospike client library will start going to that list, and the very first node it connects to, it will reach out to that node and then get the list of all nodes in the cluster, and then open direct connections to each node of the cluster. And once these connections are established, you're ready to read and write data. So this kind of shows you in various programming languages how you can open the connection and instantiate the client object. Once you have the client object instantiated, all your read-write operations occur through that client object. Now, as we discussed earlier, you need three things to find a record on a node. You need the namespace, so you can identify the correct partition map, and then you need the set name and your key to essentially compute the digest. And with that, you can go locate a record. And so on the API side, we create what you can say a key structure or a key object by giving it these three parameters: the namespace, the set name, and your key. So the first step in any read-write operation is to create that key object that will help us locate the record. So if you look at the sample Java code here, you're creating the key object. Then whatever bins you want to add or update to that record, you will use the put call to write, and you can also pass a write policy which lets you override the default write policy, and lets you do things like change the expiration time of a record or specify what to do when the record already exists. So there are a bunch of write policy options that you can overwrite when you do a write. And the example here shows you how to do a multi-bin write. We also have deletes, and in the enterprise edition we allow you to do what's called durable deletes, and that's the recommended way to delete records should you need to delete. When you use durable deletes, we write a tombstone, and that prevents zombie records from coming back to life for certain corner cases, like should you cold start a down node. So if you ever want to use deletes, we highly recommend that you use durable deletes. But for most users, they design their data model in such a way that for a given namespace, there is a record expiration time, and they let the record naturally expire at the end of its TTL, or time to live. You can also set time to live forever. So for certain namespaces, you can have records that never expire. Now let's look at the read operations. On the read side, you have the get operation. Again, you pass the key object and then the data will be fetched from the server and you consume the data. You can choose to read specific bins only to reduce the network bandwidth usage. You can read multiple records using our batch index read. You can also do secondary index queries or scan all records in a namespace and optionally just a set within a namespace. You can also do predicate filtering. So the batch operation allows you to read many records in one operation by sending an array of keys, and the records are returned in the same order as the order of keys in the array. Now, you just have to make sure that you have enough memory in the client to hold your result set. In a scan operation, you are scanning all the records in a given namespace and you can optionally specify a set in the namespace. And here, you consume the records as they arrive. So the data is pipelined. So that's the difference between scan and batch index read. You can do secondary index queries by building a secondary index on a bin of records. This applies to multi-bin records. So you can take a bin and build a secondary index on it, either numeric or string values or Geo2D sphere, and that allows you to further filter based on the value inside the secondary bin. So here you have either the equality filter for string or equality and range for numeric. This is how you would use a filter on another bin in the record and fetch a subset of records. Now, on this subset of records, you can either consume them as they come once you execute the query. So this is the syntax for executing the query. So you get a record set and you would consume as they come. Or you can additionally apply user-defined functions to these set of records obtained from a secondary index query. You can consume these records in a read-only mode to do aggregation such as computing averages, etc. Using what we call stream UDFs. Now we also allow you to use what are called record UDFs if you want to update or modify or read single records. So Aerospike allows you to write your own user-defined functions that allow you to bring essentially compute to the data. And finally, with version 3.12, we also introduced predicate filters. So you can take the results of a secondary index query and additionally filter them either on record metadata or on bin values. So you can write fairly complex queries on top of a secondary index query. In closing, I would like to invite you to explore the many clients we have available, such as Java, C, C Sharp, a whole bunch of programming languages. Pick the one that best suits your application. There is a link here to explore the APIs. We have also full day trainings available for developers, admin and ops, data modeling, cross data center replication, and I have the link to the training schedule at the bottom of the slide. Finally, if you want to get hands-on, which I highly recommend, you can download our Community Edition server at the link shown. You can download and install the Java client and build and test the sample Java application. Thank you for the privilege of your time today.